Hello class. Today we're going to review section 8.4, linear functions, graphs, and models. Alright, we need to know the meaning of the terms relations, functions, domain, range, independent variable, and dependent variable. We need to use function notation, identify a linear function and graph it, perform cost analysis to an equation using linear functions, construct a linear model from a set of data points. Let's start with relation. A relation is a set of ordered pairs. For example, the sets F equals 1, 2, comma, -1, 5, comma, 4, 3, and G equals 1, 5, comma, 9, 0, comma, 9, 8 are both relations. Okay. If the value of the variable y depends on the variable x, the y is the dependent variable and the independent variable is your x. So here, the independent variable is your x, your dependent variable is your y. That's our coordinate point there, x, y. A function is a relation in which for each value of the first component of the ordered pairs, there is exactly one value of the second component. Of the two sets, f and g, only f is a function. The reason being is for every x, there's only one y. But in G, we have the scenario for the x of 9, there are two different y's unto which it can be. Therefore, G is not a function. Only f is the function. Because you have a repeat here in your x. You have an x that can be with or a 9 that can be with a 0 or a 9 that can be with an 8. Therefore, it nullifies it as the function. Now, it doesn't work the other way around. It's okay if the y repeats. It's not okay if the x repeats. If the x repeats, you do not have a function. If the y repeats, you can still have a function. In a relation, the set of all values of the independent variable x is the domain. The set of all values of the dependent variables y is the range. So now we have defined the domain and the range. The graph of a relation is the graph of its ordered pairs. The graph gives a picture of the relation which can be used to determine its domain and range. All right, let's look at the variations of the definition of a function. A function is a relation in which for each value of the first component of the ordered pairs, there is exactly one value of the second component. A function is a set of distinct ordered pairs in which no first component is repeated. A function is a rule or correspondence that assigns exactly one range value to each domain value. All three of those are valid variations of the definition of functions. Use the one unto which your brain understands the best. All right, let's look at function notation. When a function f is defined with a rule or an equation x and y for the independent and dependent variables, we say y is a function of x to emphasize that y depends on x. We use the notation y equals f of x, called function notation, to express this and read f of x as f of x. For example, if y equals 3x plus 1, we can also write f of x equals 3x plus 1. We essentially are using y and f of x interchangeably here. Y is a function of x, and f of x is just a way to write function of x. Note that f of x is just another name for the dependent variable y. If the f of x equals 3x plus 1, we find f of 2 by replacing the x with 2. Why do we do that? Because the x is where that 2 was. That means that all these other x's needs to get replaced by 2 as well. So f of 2 equals 3 times 2, because that's we put a 2 right here. We're also going to put a 2 where all the other x's are at. So 3 times 2 plus 1. Well, 3 times 2 is 6, plus 1 is 7. Therefore, f of 2 equals 7, which essentially means when y is 2, x is 7. Now, let's let f of x be x squared plus 3x minus 1. And let's find the following. Let's find f of 2, f of 0, and f of 2x. let's start with the first one here, f of 2. Okay, f of 2. That means I need to put 2 in for all of the x's. So I'm going to do 2 squared plus 3. Oh, there's an x there. I need to replace that x with a 2. That's what we're supposed to do. Stay on task. Replace all the x's with 2's. Boom, there we go. Okay, minus 1. Now 2 squared is 4. 3 times 2 is 6. Minus 1. 4 plus 6 is 10. Minus 1 is 9. F of 2 is 9. Okay, f of 2 is 9. How about f of 0? Okay, f of 0, we can do this. I'm going to replace all the x's with zeros now. So 0 squared plus 3 times 0 minus 1. Well, 0 squared is 0. 3 times 0 is 0. So that's just negative 1. There we are. Oof, this one's weird. This is f of 2x. Well, let's just follow the same pattern here. I'm going to replace x with 2x. Everywhere there's an x, I'm going to put a 2x in parentheses. So 2x squared plus 3 times 2x minus 1. Okay, now I just have to simplify. 2 squared is 4. X squared is x squared. 3 times 2x is 6x. Then minus 1. That's it. Nothing fancy. If you see a 2 in the parentheses, you replace all the x's with 2's. If you see a 0 in the parentheses, you replace all the x's with 0's. If you see a 2x in the parentheses, you replace all the x's with 2 x's. It's that simple. And then you just simplify. All right, let's look at this. It says a function can be written in the form f of x equals mx plus b for real numbers m and b as a linear function. Okay. Let's graph each of these linear functions. Now this should look familiar because they're in that slope-intercept form. All right, f of x equals negative 2x plus 1. All right, let's see. The 1 is your b, which is your y-intercept. Okay, so let's go to the 1. Put a little dot there. This is your slope. That's your m. Slope's negative 2, which means I need to go down 2 and right 1. So that's where those points should be. Okay, we should just be able to now connect those 2 points. And hey, we have our line. That easy. How about b here? F of x equals 2. Now, we can replace f of x with y if it helps jog our memory here. Now, y equals 2. Isn't that just the horizontal line here through that 2 point on y? It is. It is. It's that simple. All right, let's look at this example. It says a company produces DVDs of live concerts. The company pays $200 for advertising the DVDs. Each DVD costs $12 to produce, and the company charges $20 per disc. We want to express the cost C as a function of X, the number of DVDs produced. And then we want to express the revenue R as a function of X, the number of DVDs sold. And then we want to find when will the company break even. That is, for what value of X does revenue equal cost? Let's start with part A, expressing the cost as a function of X. Now let's go back into the question here and look at what it cost the company to produce the DVDs. Well, it cost them the $200 flat rate for advertising, but it also cost them $12 each to produce the DVDs. So, with the fixed cost of $200, and for each DVD produced, the variable cost is $12. That means the cost C can be expressed as the function of X, the number of DVDs produced, as C of X equals 12X, so 12 times the number of DVDs produced, plus that fixed cost for advertising of $200. That's our function. It's that simple. Now, let's go back to part B, and I'm going to back up here. Express the revenue R as a function of X, the number of DVDs sold. Well, the company charges $20 per disc, so they're making $20 per disc in revenue. So the revenue function is simply R of X equals 20 times the number of DVDs they sold, which we're representing with the letter X. And that's that simple. Now, we want to know when they will break even. Well, that's whenever C of X equals R of X, okay? Which means that if I substitute in those two equations we come up with, that means it'll be a break-even point whenever 12x plus 200 equals 20x. Then, once you set those two equations equal to each other, all you have to do is solve for x. So I'm going to subtract 20x over here. So that's how I get the 8x equals 200. I'm then going to divide by 8 on both sides. It's a rough looking 8. Sorry. And 200 divided by 8 is 25. So if 25 DVDs are produced and sold, the company will break even. That's simple. Now let's look at linear models. Given data points that lie approximately on a straight line, we can develop a linear function or a linear model to describe data. So let's look at the estimates of medical cost in billions of dollars as they are shown below. Okay, so on the left-hand side of this column, we have the year from 2000 to 2004, as well as cost in billions on the right-hand side of the column, ranging from 225 billion to 297 billion. We want to find a linear function f that models the data and use the model to predict the cost in 2010. Okay, now we're going to let x equals 0 correspond to the year 2000, x equals 1 correspond to the year 2001, and so on, so that we can express the data as ordered pairs. Okay, to find a linear equation through the data, we can choose 2 points to get a slope. Okay, so in this case, we've decided to use 0, 225 and 3, 279, and we just kind of arbitrarily chose those, to be honest. If you'd chosen a different one, it would have been fine. All right, when we do that, we can find the slope between those years. Okay, so 279 minus 225 over 3 minus 0 gives us 54 divided by 3, which is 18. Okay, now since we have also have the y-intercept, obviously, because whenever x is 0, and our corresponding value will be our y-intercept. So this is actually the y-intercept point. Because we have that, and then we now have a slope, I can give you the formula straight out. It's f of x equals the slope, which was 18x, plus the y-intercept, which is 225, which was initially given to us. Okay, now let's look at part B. Part B asks, use the model to predict the cost in 2010. Well, 2010 would be year 10, okay, because we're kind of using a year count function here, because year 0 was 2000, year 1 was 2001, so 2010 would be year 10, okay? So if we let x equal 10, and we can plug 10 in for x, essentially what we're finding here is f of 10. So 18 times 10 plus 225 should render a value of 405 billion. So the model predicts that the cost will be $405 billion in 2010. That completes this lecture. If you have any questions, please don't hesitate to reach out. It's been a good semester with y'all. Appreciate you. And hopefully, I will see some of y'all in some of my other classes. Y'all take care. I'll see you next time.